June 2024. Section A. Question 1a. Distinguish between quantitative and qualitative data. Explain techniques to summarize quantitative data. Quantitative data consists of numerical values that can be measured and analyzed statistically. Examples include age, income, or test scores. This type of data is objective and suitable for mathematical operations, making it ideal for statistical analysis. Techniques like mean, median, and mode are used to summarize central tendencies, while standard deviation and variance measure dispersion. Qualitative data, on the other hand, is non-numerical and descriptive, capturing qualities such as opinions, colors, or behaviors. It is subjective and often collected through interviews, surveys, or observations. Summarization methods include categorization, thematic analysis, and frequency counts. For example, survey responses about customer satisfaction can be grouped into themes like happy, neutral, or uppy. To summarize quantitative data, graphical tools like histograms and box plots are used for visual representation. Tables with measures of central tendency and dispersion provide a clear snapshot of the dataset. For qualitative data, pie charts or bar graphs display proportions, while narrative summaries highlight key themes. Both types of data require different approaches but are essential for comprehensive analysis. Question 1b. What does harmonic mean? Calculate it from the given data. The harmonic mean is a type of average used for datasets involving rates, ratios, or inversely related quantities. It is particularly useful when dealing with situations like average speed or financial ratios. The formula for harmonic mean is hem equals frac n sum left frac f underscore I x underscore I right, where n is the total frequency and x underscore I represents the data values. Given the data, marks x 10, 20, 30, 40, 50. Frequency f2, 4, 8, 3, 3. We calculate frac fx for each row, 0.2, 0.2, 0.2667, 0.075, and 0.06. Summing these gives 0.8017. With n equals 20, the harmonic mean is frac 20, 0.8017 approximately 24.95. This result indicates the central tendency of the dataset, considering the weight of each value. Unlike the arithmetic mean, the harmonic mean minimizes the impact of large outliers, making it suitable for skewed distributions or rate-based data. Question 2a. What is a measure of position? Which measure is widely used and why? A measure of position identifies the location of a specific value within a dataset, helping to understand its relative standing. Examples include percentiles, quartiles, and z-scores. These measures are crucial for comparing individual data points against the broader distribution, such as ranking students or analyzing economic disparities. The most widely used measure is the percentile, which divides data into 100 equal parts. For instance, the 75th percentile indicates that a value is higher than 75% of the dataset. Percentiles are popular because they provide a standardized way to interpret performance, regardless of the dataset's scale. They are extensively used in standardized testing, growth charts, and financial benchmarks. Other measures like quartiles, dividing data into 4 parts, are also useful but less granular. Z-scores, which indicate how many standard deviations a value is from the mean, are more common in statistical modeling. However, percentiles remain the go-to for practical comparisons due to their simplicity and universal applicability. Question 2b. Find the percentile rank of a score of 15 in the given data. To find the percentile rank of 15 in the dataset 18, 15, 12, 6, 8, 2, 3, 5, 20, 10, we first sort the data 2, 3, 5, 6, 8, 10, 12, 15, 18, 20. The score 15 is the 8th value in this ordered list. The formula for percentile rank is PR equals left frac text number of values below x plus 0.5 text total values right times 100. Here, there are 7 values below 15. Plugging into the formula, frac 7 plus 0.5 10 times 100 equals 75%. This means a score of 15 is at the 75th percentile, indicating it is higher than 75% of the scores in the dataset. Percentile ranks are valuable for interpreting individual performance relative to a group. For example, in competitive exams, a 75th percentile rank signifies better performance than 3/4 of the test takers. This measure is intuitive and widely used in education, psychology, and workforce analytics. Question 3. A correlation does not imply causation. Do you agree? Give reasons. Yes, correlation does not imply causation. Correlation indicates a statistical relationship between two variables, but it does not prove that one causes the other. For example, ice cream sales and drowning incidents may correlate because both increase in summer, but buying ice cream does not cause drownings. The hidden factor here is temperature, which influences both variables independently. Another reason is the directionality problem. Even if two variables are related, it's unclear which causes which. For instance, higher education levels correlate with higher income, but does education lead to higher earnings, or do wealthier individuals pursue more education? Without controlled experiments, causation cannot be inferred. To establish causation, researchers use methods like randomized controlled trials or longitudinal studies. These approaches isolate variables and track changes over time, providing stronger evidence. While correlation is useful for identifying potential relationships, it is only the first step in understanding causality. Question 3b. Explain the characteristics and uses of the t-distribution. The t-distribution is a probability distribution used in statistics, especially for small sample sizes or when the population variance is unknown. It is symmetric and bell-shaped, similar to the normal distribution, but with heavier tails. These tails account for the increased variability expected in smaller samples, providing more accurate confidence intervals and hypothesis tests. Key characteristics include its dependence on degrees of freedom (dF), which adjust the shape of the distribution. As dF increases, the t-distribution approaches the normal distribution. For example, with dF equals 30, it is nearly indistinguishable from the normal curve. This property makes it versatile for different sample sizes. The t-distribution is primarily used in t-tests, which compare means between groups or assess whether a sample mean differs from a population mean. It is also used to construct confidence intervals for small samples. These applications are fundamental in fields like medicine, social sciences, and quality control, where sample sizes are often limited. Question 4. What is a composite index? Explain its construction steps with an example. A composite index combines multiple indicators into a single score to measure complex concepts like economic development or quality of life. For example, the Human Development Index (HDI) integrates income, education, and life expectancy into one metric. These indices simplify multifaceted phenomena, enabling comparisons across regions or time periods. Constructing a composite index involves 4 steps. First, select relevant indicators e.g., GDP, literacy rate. Second, normalize the data to a common scale e.g., 0 to 1. Third, assign weights to each indicator based on importance equal or expert weighted. Finally, aggregate the weighted scores using methods like arithmetic or geometric mean. For instance, the HDI uses geometric mean aggregation to balance its components. Such indices are powerful tools for policymakers, highlighting strengths and weaknesses in a concise format. However, they require careful design to avoid bias and ensure transparency in weighting and normalization. Section B. Question 5. Distinguish between primary and secondary data. State steps for organizing fieldwork. Primary data is collected firsthand for a specific purpose, such as surveys or experiments. It is tailored to the researcher's needs but can be time-consuming and costly. Secondary data, like government reports or academic studies, is pre-existing and cost-effective but may lack relevance or accuracy for the current study. Organizing fieldwork involves 6 steps. First, define objectives clearly. Second, design data collection tools e.g., questionnaires. Third, train enumerators to ensure consistency. Fourth, conduct a pilot test to refine methods. Fifth, execute data collection systematically. Sixth, validate data for accuracy before analysis. Proper fieldwork minimizes errors and biases, ensuring reliable results. For example, a health survey requires trained interviewers, validated tools, and ethical considerations. Balancing primary and secondary data optimizes resources while meeting research goals. Question 6. Identify the sampling technique, intercept, and discuss its significance. The described technique is convenience sampling, a non-probability method where researchers select readily available participants, e.g., visitors. It is quick and inexpensive, making it useful for exploratory research or pilot studies. However, convenience sampling has significant limitations. It often introduces bias, as the sample may not represent the broader population. For instance, mall-goers might skew toward certain demographics, like higher income or urban residents. Despite this, it can generate preliminary insights or test survey designs before larger studies. To mitigate bias, researchers can combine it with other methods or acknowledge limitations in their findings. While not ideal for generalizable results, convenience sampling is valuable in early-stage research or when resources are constrained. Question 7. What is a case study? How is it distinct from participatory research? A case study is an in-depth investigation of a single individual, group, event, or community to explore complex issues in real-world contexts. It employs multiple data sources like interviews, observations, and documents to provide a holistic understanding. For example, a case study on a successful startup might analyze its business model, challenges, and growth strategies to derive lessons for entrepreneurs. Participatory research, on the other hand, actively involves subjects as co-researchers, empowering them to shape the study's goals and methods. Unlike case studies, which are often researcher-led, participatory research prioritizes collaboration and shared decision-making. For instance, a health intervention study might engage community members in designing and implementing surveys to address local needs. The key distinction lies in control and purpose. Case studies aim for detailed analysis and theoretical insights, while participatory research focuses on practical outcomes and community empowerment. Both methods are valuable but serve different research objectives: case studies for exploration and theory building, and participatory research for action-oriented change. Question 8. What is a non-sampling error? Explain its various sources with examples. Definition and overview. Non-sampling errors are inaccuracies in data collection and analysis that occur due to factors other than the randomness inherent in sampling. Unlike sampling errors, which diminish with larger sample sizes, non-sampling errors persist regardless of sample size and can bias results. These errors arise at any stage of research, from design to data processing, and can significantly compromise the validity of findings. For example, if survey respondents misinterpret questions, the collected data will be flawed even if the sample is perfectly representative. Sources of non-sampling errors. 1. Measurement errors occur when data collection tools, e.g., surveys, instruments, yield inaccurate responses. Example: a faulty thermometer recording incorrect temperatures in a climate study. 2. Non-response bias, when selected participants refuse or fail to respond, skewing results. Example: a health survey where only fitness enthusiasts participate, ignoring sedentary populations. 3. Data processing errors, mistakes during data entry, coding, or analysis. Example: mislabeling, male and female categories in a demographic dataset. Mitigation and impact. Non-sampling errors are often systemic and harder to quantify than sampling errors. To minimize them, researchers can pretest questionnaires, train enumerators, and use automated data validation tools. For instance, a census might employ double-entry verification to reduce processing errors. Ignoring these errors can lead to misleading conclusions, such as overestimating product demand due to biased survey responses. Addressing them requires proactive design and transparency about limitations in the study method measures. Question 9. Is the coefficient of variation CV better than standard deviation SD for comparing dispersion? Yes, the CV is often better for comparing dispersion across datasets with different units or scales. The CV is unitless, expressed as a percentage, calculated as frac SD text mean times 100. This allows direct comparison of variability, such as height cm versus weight kilogram. For example, dataset A mean equals 50, SD equals 5 has a CV of 10%, while dataset B mean equals 200, SD equals 20 also has a CV of 10%. Despite differing SDs, their relative variability is identical. The SD alone would misleadingly suggest dataset B is more variable. However, the CV is less meaningful when the mean is close to zero, as it becomes unstable. In such cases, SD or other measures are preferable. Overall, the CV's standardization makes it superior for cross-dataset comparisons. Question 10. What is a histogram? Discuss the advantages of plotting a frequency polygon over a histogram. A histogram is a graphical representation of data distribution using contiguous bars, where the area of each bar corresponds to the frequency of values in a bin interval. It is ideal for visualizing the shape, central tendency, and spread of continuous data. For example, a histogram of exam scores shows how many students fall into ranges like 50 to 60, 60 to 70, etc., highlighting patterns like skewness or gaps. A frequency polygon, however, replaces bars with points connected by lines, plotting midpoints of bins against frequencies. Its advantages over histograms include 1. Clarity in comparing multiple datasets. Overlapping polygons are easier to interpret than stacked bars. 2. Emphasis on trends. The line smooths out irregularities, making shifts or peaks more apparent. And 3. Flexibility. It can incorporate cumulative frequencies or normalized scales without visual clutter. For instance, comparing income distributions across 2 years is clearer with frequency polygons, as lines avoid the overlap confusion of histograms. However, histograms remain better for displaying exact bin frequencies and gaps in data. The choice depends on the analysis goal: histograms for precise distribution, polygons for trend comparison. Question 11. Short notes. Epistemology, the study of knowledge origins, nature, and limits. It examines how we justify beliefs and distinguish truth from opinion. For example, empiricism relies on sensory experience, while rationalism emphasizes reason. Explanatory variable, the independent variable in regression analysis, presumed to explain changes in the dependent variable. For instance, in studying education's impact on income, education is the explanatory variable. Outlier, an extreme value that deviates significantly from other observations. Outliers can skew results, like a billionaire in an income survey. They are detected using tools like box plots or z-scores and may be removed or analyzed separately. June 2023. Section A Answers. Question 1. Quantitative research. Quantitative research is a systematic empirical investigation that focuses on collecting and analyzing numerical data. This approach allows researchers to identify patterns, test hypotheses, and establish relationships between variables through statistical methods. The emphasis is on objective measurements and replicable findings that can be generalized to larger populations. For example, a study examining the relationship between study time and exam scores would use quantitative methods to collect numerical data and analyze correlations. The key attributes of quantitative research include its structured methodology, use of measurable variables, and reliance on statistical analysis. Researchers employ standardized instruments like surveys with closed-ended questions to ensure consistency in data collection. The large sample sizes typically used in quantitative studies enhance the reliability and generalizability of findings. This makes quantitative research particularly valuable in fields like medicine, psychology, and social sciences where precise measurements and statistical validity are crucial. Common data collection tools in quantitative research include surveys, experiments, and observational checklists. Surveys with Likert scales or multiple-choice questions provide structured responses that are easily quantifiable. Controlled experiments manipulate variables to establish cause and effect relationships, while observational methods systematically record behaviors or events. Secondary data sources like government statistics or organizational records also serve as valuable resources for quantitative analysis, offering large datasets for researchers to examine. Question 2a. Mean and standard deviation. The mean height of the 7 plants is calculated by summing all individual heights and dividing by the number of plants. Adding the given heights 52, 35, 25, 45, 55, 20, and 13 centimeters gives a total of 245 centimeters, which when divided by 7 plants yields a mean height of 35 centimeters. This average provides a central value representing the typical height of plants in the sample, offering a quick understanding of the data's central tendency. Standard deviation measures how much individual plant heights vary from this mean. To calculate it, we first find each plant's deviation from the mean, square these values to eliminate negative differences, and then average these squared deviations. The square root of this average, approximately 14.46 centimeters, gives the standard deviation, indicating that most plant heights fall within about 14.46 centimeters of the mean. This measure helps understand the dispersion of data points around the central value. These calculations are fundamental in descriptive statistics, providing insights into both the typical value mean and variability standard deviation within a dataset. In practical terms, knowing that the average plant height is 35 centimeters with a standard deviation of 14.46 centimeters tells us that while some plants are much taller or shorter than average, most cluster reasonably close to the mean height. This information could be valuable for gardeners or biologists studying plant growth patterns. Question 2b. Histogram. A histogram provides a visual representation of how plant heights are distributed across different ranges or bins. For this dataset, we might create bins of 10 cm intervals 10-20 cm, 20 to 30 cm, etc., and count how many plants fall into each range. The resulting bars would show that 2 plants are between 10 to 20 cm tall, 13 and 20 cm, 1 plant between 20 to 30 cm, 25 cm, and so on, with the tallest bar likely appearing in the 50 to 60 cm range, 52 and 55 cm. The histogram's shape reveals important characteristics about the data distribution. In this case, we might observe that the heights are somewhat evenly spread across the range rather than clustering tightly around the mean. The graph might show a slight right skew, with more plants appearing on the shorter side of the scale. This visual tool helps quickly identify patterns that might not be obvious from numerical summaries alone. Creating such histograms is particularly useful when dealing with larger datasets, where visual patterns become more meaningful. They allow researchers to spot potential outliers, understand the data's symmetry or skewness, and make initial assessments about whether the data follows a normal distribution. These insights can guide further statistical analysis and help communicate findings more effectively to diverse audiences. Question 3a. Measures of dispersion. Measures of dispersion quantify how spread out the values in a dataset are, providing crucial context to measures of central tendency like the mean. While the average gives a typical value, dispersion measures tell us how representative that average is of the entire dataset. Common measures include range, variance, standard deviation, and interquartile range, each offering different perspectives on data variability. The importance of dispersion measures becomes clear when comparing datasets with similar means but different spreads. For instance, 2 classes might have the same average test score, but one class's scores could cluster tightly around the average while the other's scores are widely scattered. Understanding this difference is essential for accurate interpretation of results and making informed decisions based on data. In practical applications, dispersion measures help assess risk, quality control, and reliability. Financial analysts use them to evaluate investment volatility, manufacturers to monitor product consistency, and researchers to determine the precision of their measurements. Without considering dispersion, one might draw misleading conclusions from data that appears similar at first glance but actually contains important differences in variability. Question 3b. Absolute and relative measures. Absolute measures of dispersion express variability in the original units of measurement, making them intuitive to interpret but difficult to compare across different datasets. The range simply calculates the difference between maximum and minimum values, while variance and standard deviation provide more sophisticated measures that consider all data points. These absolute measures are particularly useful when working with a single dataset where maintaining original units is important. Relative measures like the coefficient of variation (CV) standardize dispersion by expressing it as a percentage of the mean, enabling comparisons between datasets with different units or scales. For example, comparing height variability measured in cm with weight variability measured in kilogram becomes possible using CV. These relative measures are invaluable when assessing consistency across diverse measurements or when the absolute size of values varies significantly. The choice between absolute and relative measures depends on the analytical goals. Absolute measures work best for understanding variability within a specific context, while relative measures excel in comparative analyses. Both types complement each other, with absolute measures providing concrete understanding and relative measures facilitating broader comparisons across different studies or measurement systems. Question 3. C. Most reliable measure. Standard deviation stands out as the most reliable measure of dispersion for several important reasons. Unlike simpler measures like range, which only considers extreme values, standard deviation incorporates every data point in its calculation. This comprehensive approach makes it less susceptible to distortions from outliers and more representative of the entire dataset's variability. The mathematical properties of standard deviation further enhance its reliability. By squaring deviations before averaging them, it gives greater weight to larger deviations while maintaining the original units of measurement when we take the square root. This balance between sensitivity to variation and interpretability makes standard deviation particularly valuable in statistical analysis and hypothesis testing. In practical applications across various fields, standard deviation has become the gold standard for measuring dispersion. From psychology experiments to quality control in manufacturing, researchers and professionals rely on standard deviation to assess consistency, predict ranges of normal variation, and make data-driven decisions. Its widespread adoption and mathematical robustness make it the most trustworthy choice among dispersion measures. Question 4. Non-sampling errors. Non-sampling errors represent inaccuracies that occur in data collection and analysis processes, unrelated to the randomness inherent in sampling methods. These errors can arise from various sources including flawed measurement instruments, respondent biases, data processing mistakes, or poor questionnaire design. Unlike sampling errors that decrease with larger sample sizes, non-sampling errors may persist regardless of sample size and can significantly distort research findings. The impact of non-sampling errors can be substantial, potentially leading to incorrect conclusions and misguided decisions. For instance, if survey questions are ambiguously worded, respondents might misinterpret them, leading to systematically biased responses. Similarly, data entry errors might create artificial patterns in the dataset that don't reflect reality. These errors are particularly problematic because they often go undetected in standard statistical analyses. Mitigating non-sampling errors requires careful planning and quality control throughout the research process. Strategies include pre-testing survey instruments, training data collectors thoroughly, implementing data validation checks, and maintaining transparency about potential limitations. While it's impossible to eliminate all non-sampling errors completely, awareness of their sources and proactive measures to minimize them can significantly improve data quality. And research observation. Q4b Research observation. Kurtosis and its measures. Kurtosis is a statistical measure that describes the shape of a distribution's tails in relation to its overall shape. It specifically measures whether the data are heavy-tailed or light-tailed relative to a normal distribution. A distribution with high kurtosis tends to have more outliers, indicating fatter tails, while low kurtosis suggests fewer outliers and thinner tails. There are three types of kurtosis: mesokurtic normal distribution, leptokurtic sharper peak with fatter tails, and platykurtic flatter peak with thinner tails. Visualizing these with a Diagram helps in understanding how data points are distributed around the mean. The most common measure of kurtosis is the fourth standardized moment, calculated by taking the fourth power of deviations from the mean and normalizing it. Excess kurtosis, which compares the kurtosis of the distribution to that of a normal distribution, is often used for easier interpretation. A positive excess kurtosis indicates a leptokurtic distribution, while a negative value suggests a platykurtic distribution. These measures are crucial in fields like finance, where understanding tail risks can prevent significant losses. Kurtosis is particularly important in data analysis because it provides insights into the probability of extreme values. For example, in quality control, a leptokurtic distribution might indicate a higher chance of defects, while in investment, it could signal greater risk of extreme returns. By analyzing kurtosis alongside skewness, researchers can gain a comprehensive understanding of a dataset's shape and potential anomalies. Question 5. Type 1 and Type 2 errors in hypothesis testing. Type 1 and Type 2 errors are fundamental concepts in hypothesis testing that represent different kinds of mistakes researchers can make. A Type 1 error occurs when we incorrectly reject a true null hypothesis, essentially finding an effect that doesn't actually exist, false positive. This is often considered more serious in many scientific contexts because it could lead to implementing ineffective treatments or policies based on incorrect findings. The probability of making a Type 1 error is denoted by alpha, which is typically set at 0.05 in many research fields. A Type 2 error happens when we fail to reject a false null hypothesis, meaning we miss detecting a real effect that does exist, false negative. The probability of this error is called beta, and its complement 1 beta represents the test's power. While less immediately dangerous than Type 1 errors, Type 2 errors can be equally problematic in the long run by causing researchers to overlook important discoveries or treatments. The balance between these two types of errors is crucial in research design, as reducing one typically increases the risk of the other. In most research contexts, Type 1 errors are considered more critical, because they lead to false claims of discovery, which can have serious consequences in fields like medicine or public policy. However, the relative importance depends on the specific situation. In medical screening tests, for example, a Type 2 error missing an actual disease might be considered more dangerous than a Type 1 error, false alarm. Researchers control these risks through careful experimental design, appropriate sample sizes, and by setting significance levels that reflect the consequences of each type of error. Question 6. Distinctions between key concepts. A cross-section data and panel data differ fundamentally in their structure and analytical potential. Cross-section data captures information from multiple subjects at a single point in time, providing a snapshot of a population. For example, a survey of 1,000 people's incomes in January 2023 would be cross-sectional data. Panel data, by contrast, follows the same subjects over multiple time periods, allowing researchers to track changes at the individual level. This longitudinal approach is more valuable for studying causal relationships and temporal patterns, though it's more expensive and time-consuming to collect. The null hypothesis H and alternative hypothesis H form the foundation of statistical testing. The null hypothesis represents a default position of no effect, or no difference, that researchers aim to challenge. For instance, H might state that a new drug has no effect on blood pressure. The alternative hypothesis expresses what the researcher actually believes to be true, that the drug does affect blood pressure. The entire hypothesis testing framework is built around determining whether there's sufficient evidence to reject the null hypothesis in favor of the alternative. See descriptive and inferential. Statistics serve different but complementary purposes in data analysis. Descriptive statistics summarize and organize data through measures like means, medians, and standard deviations, along with visual tools like histograms. They help researchers understand what the data look like. Inferential statistics, on the other hand, allow us to draw conclusions about populations based on sample data, using techniques like hypothesis testing and confidence intervals. While descriptive statistics tell us about our specific dataset, inferential statistics help us make broader generalizations and predictions. Question 7. Bivariate analysis and related concepts. A bivariate analysis examines the relationship between two variables to identify patterns or associations. This can involve looking at correlations between continuous variables like height and weight, comparing means across groups like test scores between genders, or examining contingency tables for categorical variables. The choice of specific techniques, scatter plots, t-tests, chi-square tests, depends on the nature of the variables being analyzed. Bivariate analysis serves as an important first step in understanding potential relationships before moving to more complex multivariate analyses. B. The relationship between correlation and causation is often misunderstood. Correlation simply means two variables change together in some predictable way, but this doesn't necessarily imply one causes the other. They might both be influenced by a third variable, or the correlation might be coincidental. Establishing causation requires additional evidence beyond correlation, typically through controlled experiments that eliminate alternative explanations. This distinction is crucial because mistaking correlation for causation can lead to flawed decisions and policies based on superficial relationships. C. The choice between z-tests and t-tests depends on specific conditions of the data being analyzed. Z-tests are appropriate when we know the population standard deviation and have a large sample size, typically n greater than 30, relying on the normal distribution. T-tests are used when the population standard deviation is unknown and sample sizes are smaller, using the t-distribution, which has heavier tails, to account for additional uncertainty. Both tests compare means, but the t-test's flexibility makes it more commonly used in real-world research, where population parameters are rarely known exactly. Question 8b. Skewness and kurtosis in distribution shape. Skewness and kurtosis together determine the asymmetry and tail behavior of a distribution, respectively. Skewness measures the degree of asymmetry, where positive skew indicates a longer right tail, and negative skew means a longer left tail. Kurtosis, on the other hand, measures whether the data are more or less outlier-prone than a normal distribution. Together, they provide a complete picture of how data are distributed around the mean. For instance, a positively skewed distribution with high kurtosis would have most data points clustered on the left with a few extreme values stretching to the right. This combination might appear in income data, where most people earn moderate amounts, but a few have significantly higher incomes. Understanding these measures helps in selecting appropriate statistical tests and models, as many analytical methods assume normal distribution. In practical applications, skewness and kurtosis inform decisions about data transformation or the need for non-parametric tests. For example, if data show high skewness, applying a logarithmic transformation might normalize it. Similarly, high kurtosis might prompt researchers to investigate potential outliers or consider robust statistical methods less sensitive to extreme values. Question 9a. ANOVA and its usage. ANOVA, analysis of variance, is a statistical method used to compare means across multiple groups to determine if at least one group differs significantly from the others. It works by analyzing the variance within groups versus the variance between groups. If the between-group variance is significantly larger than the within-group variance, it suggests that the group means are not all equal. ANOVA is widely used in experimental research to test the effects of different treatments or conditions. The primary advantage of ANOVA is its ability to handle multiple groups simultaneously, reducing the chance of type 1 errors that might occur with multiple t-tests. For example, in agricultural research, ANOVA could compare crop yields across several fertilizer types, controlling for other variables. It provides an f-statistic and p-value to assess whether observed differences are statistically significant. ANOVA has several variants, including one-way ANOVA for a single independent variable and factorial ANOVA for multiple independent variables. Post hoc tests, like Tukey's HSD, are often used after a significant ANOVA result to identify which specific groups differ. This makes ANOVA a versatile tool for hypothesis testing in fields ranging from psychology to engineering. Question 9b. ANOVA versus MANOVA. While ANOVA compares means of a single dependent variable across groups, MANOVA, multivariate analysis of variance, extends this to multiple dependent variables analyzed simultaneously. MANOVA is useful when researchers want to understand the effect of independent variables on several interrelated outcomes. For example, in educational research, MANOVA could assess how a teaching method affects both test scores and student engagement. MANOVA accounts for correlations between dependent variables, providing a more comprehensive analysis than separate ANOVAs. It uses multivariate test statistics like Wilks, lambda or Pilet's trace to determine significance. However, MANOVA is more complex and requires larger sample sizes to maintain statistical power, making it less suitable for small datasets. The choice between ANOVA and MANOVA depends on the research question. If the focus is on a single outcome, ANOVA suffices, but for understanding complex, multidimensional effects, MANOVA is more appropriate. Both methods assume normality, homogeneity of variance, and, in MANOVA's case, homogeneity of covariance matrices. Question 10a. Participant observation. Participant observation is a qualitative research method where the researcher immerses themselves in a group or community to study it from within. This approach allows for deep understanding of behaviors, norms, and social dynamics that might not be apparent through surveys or interviews. For example, an anthropologist living with a tribal community to study their customs employs participant observation. The advantages include rich, contextual data and the ability to capture subtle, unspoken aspects of social life. However, drawbacks include potential bias, as the researcher's presence might influence group behavior, and the time-intensive nature of the method. Ethical considerations, such as informed consent and maintaining objectivity, are also crucial. Despite its challenges, participant observation provides insights that other methods cannot. It's particularly valuable in exploratory research or when studying closed or complex social systems where external perspectives might miss key nuances. Question 10b. Non-participant observation. Non-participant observation involves researchers observing a group without actively participating in its activities. This method removes the potential influence of the researcher on the group's behavior, addressing a key limitation of participant observation. For example, a psychologist might observe children's playground interactions from a distance to study natural social dynamics. The main advantage is increased objectivity, as the researcher remains separate from the observed group. However, this distance might limit understanding of internal perspectives or motivations. Non-participant observation is often used when complete neutrality is essential or when participant observation would be impractical or unethical. Combining both methods can provide a balanced view, participant observation for depth and non-participant observation for objectivity. The choice depends on the research goals and the nature of the group being studied. Question 11. Short notes. 8 degrees of freedom. Degrees of freedom refer to the number of independent values in a statistical calculation that can vary. In hypothesis testing, they affect the shape of distributions like t-distributions and are crucial for determining critical values. For example, in a t-test, degrees of freedom are calculated based on sample size and influence the test sensitivity. B. Coefficient of determination R squared. R squared measures the proportion of variance in the dependent variable explained by the independent variables in a regression model. An R squared of 0.8 means 80% of the variance is explained by the model. While useful, it doesn't indicate causality and can be inflated by adding more predictors. See Focus Group Discussion FGDs. FGDs are structured group interviews exploring participants' views on a specific topic. They generate qualitative data through group interaction, revealing consensus, disagreements, and diverse perspectives. Moderators guide discussions while ensuring all voices are heard. D. Grounded theory. Grounded theory is a qualitative research method where theories emerge from data rather than being tested. Researchers iteratively collect and analyze data to develop concepts and relationships. It's particularly useful in exploratory studies where little prior theory exists. These methods and concepts are fundamental across research disciplines, each offering unique strengths for different investigative needs.